As the global market segment leader, Thornton provides global direction for marketing, sales, business, and technical matters for the Chemours immersion cooling, fire extinguishant, pharmaceuticals, and electronic gas business platforms. Mr. Thornton has been involved with the development, use, and application of fluorinated gases for more than 30 years. He is well recognized across the globe as an authority for these products and sits on a variety of code of standard bodies as well as various industry and trade associations. In today's fireside chat, we will be discussing the trends in thermal management of data centers and the next generation of advanced cooling techniques. That's quite a mouthful, and you know what all of those words mean.
Absolutely, Deborah. It's been an interesting ride, and I think as we discussed talking about trends in this particular space, I did want to take a little bit of a 30,000-foot view, perhaps. The last couple of speakers and presentations I've watched. We've talked a lot about the details of anything in particular, and with my background being multiple industry segments, multiple markets for many years, I think this would be a good opportunity to sort of take a more philosophical, large picture view of what's going on in the technology data center market. So
to do that, why don't you tell us about your own professional journey? How did you come into this field of liquid cooling, and also a brief history of your organization's work in this field?
Sure, thank you. Well, my background is chemical engineering. I'm a chemical engineer by trade, and chemistry is sort of in my blood, if you will. So I do come at a lot of this from a slightly different perspective. I've been dealing in these types of chemistries, both on thermal management, but even more so in the last 30 years in fire protection. So clean agent fire extinguishants from halons to FM200 for high-valued assets like data centers. That's sort of how I back-ended into the immersion cooling side, is coming at it from a fire protection standpoint.
From fire to cooling. And could you tell us a bit about what your organization does?
Well, Chemours, many people don't know Chemours as a company, but we are the chemical business of DuPont, which has a much more familiar name. And we've been doing thermal fluids as DuPont since the introduction of freons back in the 1950s. So we've been engineering thermal fluids as an organization for over 70 years now. And that's in part how we've found ourselves at the bleeding edge of data centers and compute with two-phase immersion cooling.
Exciting. So let's do a little bit of crystal ball gazing now. If you see 5 years into the future, how do you see liquid cooling technology evolving?
Well, I think it's easy to look at what we've done and see where the trends are going. There are a couple of industry trends I think we all take for fact. When we started doing data centers, we used air, right? So we're standing in a room full of air. Air is plentiful, it's cheap, we know how to push it around, and we've been very successful in technology to use this air to move heat, right? We're taking heat from a computer and we're moving it from point A to point B so that computer can run efficiently. And that's worked. As energy levels in data centers have increased, we've tweaked air to move it faster, to move it directionally. We've done some things to be able to use air to move heat from point A to point B a little bit more efficiently than perhaps we're doing today in this room. But on the technology side, we have largely, and I think one of the previous speakers had mentioned, we've pretty much reached the wall of capacity to move heat using air from today's technology. We are at the end of air's capability, strictly from a physics standpoint. Air as a material has a very low capacity to store heat. It's not a very good heat transfer fluid. But we've been able to make it work, but we've hit this wall where we can't push any more heat from point A to point B using air. So we moved to fluids. And when you move into the world of liquefied fluids, you can increase your heat capacity. Simply moving from air to water would improve your heat capacity, your ability to move heat from point A to point B, but we certainly don't want to put water into an electronic application. That doesn't work. So we look at alternative fluids. And then with the alternative fluids, we look for molecules, structural molecules that have the best capability to hold heat, to move it most efficiently. Obviously, we're trying to improve our efficiency. But even with liquids, we can still reach limitations. And one of the things we've done that's rather unique is we've started at the other end of the pipe and said, what do we want to do with this heat, and what do we need to do it? And re-engineered the system backwards from achieving a goal to what should the chemistry and physics be. And for those of you who get interested in the more science of chemistry and physics, those of you who know, when you take a liquid phase product and you convert it into a gas, you change its state of physical being, you dynamically expand the capacity of any molecule to hold heat. Your water will hold more heat as a vapor than it will as a liquid. So that was one of the key factors of basically looking at taking a highly engineered thermofluid and turbocharging it by getting it designed to work at a temperature range within its transitional state from a physical standpoint. So by taking a liquid at the right that boils at the right temperature and allowing it to convert to a gas, we've just added extra capacity to move heat to that fluid. And that's what we're doing with two-phase liquid immersion, right? We have both an engineered fluid with a very high heat capacity that will also boil at a temperature, change state from gas to liquid at a place that is where we're working. Our fluid boils at 50 degrees C, not 100 like water. So you get that phase shift, allows you to carry more heat. And that's, when you look at the trends on the technology side, and as everybody said, tomorrow we're going to need to move more heat. And the day after that, we're going to need to move more heat. And in 5 years now, we're going to be moving even more heat as the power increases on this technology.
So, but then what would you advise data centers owners and operators who are looking to transition from air to liquid cooling?
Well, so again, we've spent 40 years doing air. If you drive down Data Center Boulevard in Mumbai, right? All the boxes look the same. The architecture of what we do with air in a data center, the brands change, the models change, the performance changes. Everybody's got their own flavor, their own bells and whistles, if you will. But the architecture of a data center is fundamentally the same anywhere you go in the world. When you shift to liquid, you bring in an opportunity to change how you think about the architecture of a data center. And I think that's where it gets really interesting today, where we are between the technological leap we're making from an IT standpoint, when we're moving into these next gen chips that suddenly we're looking at AI, we're looking at doing things on a chip that we just simply weren't able to do until now. And then if you change the architecture of where and how we do that as a data center, if we're no longer constrained to a big box, to a Walmart box, if we can do the architecture different with the capabilities and technologies of the chips, where do we go? What does that look like? And I think I was having a conversation earlier. We all have these, right? When they started, they were phones. This was an alternative to finding a wire stuck to the wall with a dial to call your mother.
Now right? Nobody calls their mom.
I have a 17-year-old who has had several of these. He does not know how to use the phone function. He does not phone. He does not call. He will WhatsApp me, text me, send me an Instagram. He will do any number of things, but this is not a phone to him. The technology or the application technology of taking what used to be a supercomputer and putting it in your pocket and making it mobile has changed an entire lifestyle. And I think if we look at taking a data center, 5-story Walmart box, fixed into a place forever, take it into a smaller size, which we can do with liquid, make it mobile, and move it around, change the architecture, what we're going to do with those data centers, I think, is going to change. I don't know what it's going to look like. I don't know what you are going to figure out to do with that type of technology, but I do think it's going to be, we're going to think of this as a data center somewhere that's smaller, more compact, and more mobile. But the reality is we're going to take those features and benefits and we're going to apply them to do something that we've never done before. And I don't know what it is. But this is sort of the metaphor technology. This isn't a phone. We built it to be a communicating device to call your mother rather than having to go find a phone somewhere stuck to a wall on the end of a cable. But that's not what this is. We've changed its application and usage. You can do so many things with this that you never did with a phone. And I think a small, compact, high-powered mobile data center is going to do so many more things than what we think of as compute. I just don't know what they are.
But then, how do you go about choosing what liquid cooling technology works best for your data center? What should owners and operators be mindful of?
Well, I mean, the parameters of data center discussion are what they are. How much is it going to cost me? Where am I going to put it? What's it going to cost to run it, right? So those are fundamental business metrics that are not changing. We have to answer all those questions. The liquid cooling technologies are in the process of getting those answers right now because we've not got a lot of experience using them. The more experience we have, the more accurate those numbers will be. But if you're looking at where is my data center going to be tomorrow, 5 years out, 10 years out, and what's it going to cost me to get there, and what am I going to deliver when I get there, you have to start looking at these liquid systems. And you have to start building them into your methodologies of evaluation and thinking, what's it going to cost me today, but what am I going to get tomorrow? So this is not unlike you're used to on the chips. You're not buying H100 chips for a bargain, right? You're paying a premium for the bleeding edge today. But 3 years from now, H100s will be going for pennies a pound. And we'll be on to the next one. The cooling technologies are much the same. Liquid cooling, two-phase liquid cooling, they're still the Ferraris of our current design. They give you things that you cannot do with a conventional Ford. They are Ferraris and they cost like Ferraris, but they're Ferraris. They will get you places in a way that you cannot get to in any other way. Tomorrow, they will become standard technology. So I think if you're looking at it today, you have to understand what you get, how much it's going to cost you, what the timing is, and when you need a Ferrari. So those are the sort of the philosophical questions as an IT guy you have to start thinking. Do I need it today? Maybe, maybe not. Will I need it tomorrow? Probably. Will I be doing this as a course of business as normal operations in 5 years? I think so.
Speaking of the crystal ball, I was going to ask you another question about what happens 5 years from now, especially in wake of the AI boom. There is AI, then we add to that evolution of the liquid cooling technology. What will data centers look like 5 years from now?
Well, I think I've sort of bled into that conversation. I don't know, but we know what a data center looks like today, right? You can drive through any major hub city or outside of the city.
Scary buildings, no windows. It sometimes looks like a detention center.
Absolutely. It's either a 5-story prison or it's a data center. That's our architecture, and it works. I mean, up till today, it has worked. It's been cost effective. It's been efficient. It does the job. But when you add chip capacity into the mix, and the next ones are not going to be modestly better. The next ones are going to be exponentially better and exponentially better. When you add that into the mix and you bolt on things like AI capability, language learning modules, and some things that we haven't even figured out how to do with the technology yet, you put that into the mix. I think for those who are data center design engineers, you have to go back to a whiteboard. You have to go back to white space and look at it as a blank page. We don't have to build a box. We don't have to put it in a field on a T1 line, right? Some things are changing that allow us to reinvent what the space should look like to do the job we want to do with it. And then the job's going to evolve that we're doing with it to evolve the space even more. I mean, this is a chicken and an egg cycle, right? We build a box to do a job that we think we know what the job is going to be, and then the job changes once we get the box running, and then we have to sort of modify the box to handle the change that the technology's done. At this point, we're going to start with a white piece of paper, preferably probably with a grid, but maybe not even with a grid on it, and start thinking about what should it look like, using all of these different tools to start doing what we want the technology collectively, the whole environment, to do. And I think I'm on the molecule side, right? I'm a molecule bender, but I think for those of you on design and in the design space, this is a wild time to be playing in the game. You've been designing boxes for 20 years. Tomorrow's not going to be a box. Tomorrow's going to be something different. And some of them will be wrong and some of them will be right. And, we will learn and evolve and change as we go. But what a great time to have that white piece of paper and a pencil and a draftsman's triangle to try and figure out what should it look like.
But wouldn't you say it would be perhaps wiser in that case to sort of wait and watch a bit? I mean, is there a correct answer? Is there one correct answer? Or will the questions change by the time we find the answers?
I think we all know the questions will change, right? Anybody in any industry or any application that has gone through a technology transition, and certainly this space has done it multiple times along the way. My experience, I manage a pharma business, I manage an aerosol business, I manage our fire business. I've seen all of these industries go through that process of steady state growth, large change, make a left turn, do something entirely different. There are all sorts of people in those environments. There are first movers who are at the bleeding edge. There are followers all the way in the back who are the last ones to change, kicking and screaming. And there's the vast majority in the middle that are trying to find their way through that chaotic transition period. I think you have to figure out who you are in that humanity. Are you a bleeding edge? Do you want to drive the Ferrari, with all its benefits and its risks, right? Driving a Ferrari is risky. They have a tendency to go crash. Or do you watch and wait? And at what point do you jump in and accept? I think everybody has to look at what they're doing, but that's that analogy of, am I the organization that drives the Ferrari? Do I want to be that? Do I want to take that risk? Then, you're already moving towards two-phase liquid and, the next gen chipsets and trying to figure out how they do. But that's not for everybody. I think the speaker in the earlier talk had said, we're going to have conventional air data center systems running conventional processes for a long, long, long time. They'll always be with us. But they're going to be less and less important in the grand scheme of the infrastructure. And we're all going to be moving towards these next gen technologies, including in the air, in the cooling. I shouldn't even say air, including in the cooling space and heat management space. So I do think you need to know how the Ferraris work. You need to know what the features are. You need to know what the benefits are. You may not be ready for one yet. but you need to be doing your homework to have that in your pocket so that you know when it's time, the time is right for what you're doing to jump in.
Perfect. And it is time to call an end to this discussion. Thank you so much for joining us today. Al Thornton.